There are no penalties for not replying today, but besides embarrassment, I'm calling your name out and you're not responding. So don't be embarrassed. Okay. We're going to start on a new series of lectures. Any questions from the topic so far? I had my office hours yesterday. It was not an office hour, it was an office 10 minutes because in the last 50 minutes nobody turned up. And so I'm assuming that, considering that nobody actually turned up to ask any questions, I'm assuming that all of you imagine you understood everything so far. But here's your last chance to ask any questions about things we've covered so far. A couple of minutes. Any questions? Folks on Zoom, any questions? No, okay. Let's begin, right? Why is this guy? No. Everything must die at me. Okay. It has new batteries. Oh well. Okay. So the story so far, here's what we have seen. We've seen that pattern classification tasks such as, does this picture contain a cat? Or does this recording include a hello, are best performed by? Wait, this is, how did I get here? This is the wrong lecture. Memory. Open number 1. So we're going to be talking about scanning for patterns. Wait. What's going on? Yeah, that is. Okay. So we're going to be talking about scanning for patterns. What we've seen so far, MLPs are universal approximators. They can model any kind of function, be it Boolean, a classification problem, or a regression problem. They can be trained through variants of gradient descent. And in the model that we have seen so far, we have generally had an MLP of this kind, which can recognize patterns in data like digits or pretty much any other vector data. But here's a new problem. You have a recording of a signal, which you may have represented as a sequence of spectral vectors. And now the question is, does this recording contain the word welcome? Now, easy enough, it's a binary classification problem. If you knew the exact length of every recording, then all you would do is collect a bunch of recordings with the word welcome and a bunch of other recordings without the word welcome, and then you just train an MLP of this kind, which analyzes the entire recording and tells you the answer, right? Now, here's the problem. These two recordings both contain the word welcome. But in one case, the word welcome is on to the left, and the other case, the word welcome is to the right. Will a network that has been trained to recognize words, that is able to recognize words with welcome to the left, also be able to recognize welcome to the right? What do you think? So Pokemon Pineko, what do you think? Pineko is not around. Okay. Anybody else? Hello. Yeah, okay. What is the answer?
I think it should be able to find it. Like I'm just analoging it to a image where, like, if my object of interest is on the top right or the bottom left, a neural network should still be able to find it.
Why would you think so?
If certain activations are like making the final output one, like the location should not matter spatially, is what I'm thinking.
Okay, so here's a chart. I'm looking for a chart. So let me simplify the problem for you. Suppose I have a network which has been trained to recognize Now, will this recognize also fire if the input is this? Yes or no? Why not? They live in completely different spaces. The first one is in the YZ space. The third one is in the 7th and 8th dimensions, right? So, going back, so a picture, a network that recognizes the first image, the first welcome, will it recognize the second welcome? No, right? So, this is not going to work. And so we need a simple network that will fire regardless of the location of the word, and clearly says simple MLP is not going to do the job, right? And it must not fire when the word is not present. Similarly, flowers, right? Here are a collection of images. Some have flowers, some have flower-looking objects, but they're not flowers. And so, if I train an MLP to look at pictures, and if it's able to recognize flowers, images when they occur to the top left, will the same network be able to recognize the flower if it's to the bottom right?
Not unless you have like sufficient examples of both.
So basically, the first network, the network will not be able to recognize the second flower unless the second flower is also part of your. How many different positions can you have for flowers? How much training data will you require? And how large will your network be for all of this? Very large, right? So again, we have the situation where you want a network that will fire regardless of the precise location of the target object and must still be simple, right? So this gives us a need for shift invariance, meaning in many problems the location of the pattern is not important, only the presence of the pattern is. And conventional MLPs are sensitive to the location of the pattern. They are basically completely different subspaces, right? And so if I just move my pattern by one position, you live in a completely different subspace. Instead of having a feature along, component X, now we have a feature along component Y, and so they will not fire. But we want a network to be shift invariant. It should not care where the object is in the image, right? So how would you solve for this? Anyone? Does somebody want to tell me how we would solve for it? So who's that? Hoot Hoot. Who's Hoot Hoot?
Oh, it's me.
Okay. How would you solve for this?
I guess you can like create like a mask to mask out like certain stuff that's not like relevant.
Yeah, but then how would that solve the problem of position invariance?
Because then if you like mask out everything else and then just look at the part in the mask.
But then if the object has gone to the right, it's going to be completely masked. Will it not?
Yeah, but then you can shift the mask around too.
Shifting the mask around. So how do I know where to shift the mask to? So somebody else want to give me an answer?
Move it all across the.
So here's what anyone answers. Zoom.
Yeah. Can you hear me?
Yes.
Okay. My proposition should be that all the images will just contain flower, centroid, and there will not be anything else.
The
So
problem is
sky.
how would you know where to center it? You wouldn't, right? So the solution that you would need to do is to perform what some of the rest of them have suggested, is to scan. If I know the approximate size of the word welcome, I'm going to build a network that will look at just that segment of the input, and then I can scan left to right. And at each position, it's going to tell me if the word welcome has occurred or not, right? But then I have another problem. I have an answer at every one of these locations, But the question to which I'm actually trying to find an answer is, does the word welcome occur anywhere in the recording? So how do I combine these to get that answer? Zapdos, Pokemon Zapdos, what's the answer here? Zapdos is not present, okay? So, Elekid, what's the answer? Not present, okay? Pikachu, you've got to be around. Everybody, Pikachu is always around. So what is the answer to this?
You can um, try to combine them in some way.
How do you combine them? Anyone else? Yes.
Like a majority vote. Like
A majority vote. Why do I need a majority vote? It's just an OR logic. I pick the max. If any one of them has fired, the max is a 1, right? And so that's all I really need to do. And I could sort of improve on the max by adding a perceptron over here, which looks at maybe adjacent windows as well. Or if I'm so inclined, yes.
Are you saying we have a different network for each?
No, you're scanning. It's the same network. Scanning it. You're scanning it, right? You're getting an answer at for each position. Right? And so, or I can even replace this with a full MLP, right? So if I were to write pseudocode, this is what it's going to look like. Yes.
Okay, so why are we using the perceptron as the final layer? What difference does that make?
Things get, if something shifts by 1 pixel, is it not a flower anymore? So the fact that you're going to have adjacent things firing typically means you need a little more complex logic. That's all fine. And so, or you can have a full MLP. But the point is this: what I'm doing is starting with my network. I'm scanning left to right. At each position, I am pulling out a segment of the input and passing it through an MLP. And the collection of outputs is being put through my softmax to decide if there's a flower present. Yes, Lawrence?
So this is like shifted variant, right? Yeah.
We get to that much later. Okay. And so, but then if you look at it, this is just one giant network. I have a bunch of networks, all giving you an answer at each location, and their outputs are being put through a perceptron or an MLP. So this is just a giant network. What is special about this network?
The size is much smaller than probably where we
What is special about this network? So again, tell you what it is. This is just this whole thing is just a network. I could have just written giant MLP with one difference. It's a shared parameter network, meaning all the subnets at the bottom are identical, right? That's what's special about this network. I have a collection of subnets, all of them are identical, and their outputs are going into the final decision layer, right? Same thing with the 2D case. I can create a little MLP which looks at one small location in the image, and I can scan bottom to top, left to right, right? And then eventually I can pass all of their outputs through an MLP, through a final perceptron or even an MLP, and it decides if there's a flower in the picture. Now in both cases, this is once again just a giant network, right? The specialty over here is that this network, by virtue of having identical subnets at every location, is what invariant? Shift invariant. It is going to fire regardless of the position of the object in the image. Everybody with me? Right, okay. So, once again, I can just write the whole thing. What are we really doing? We are scanning left to right, right? Top to bottom. Sarthak's answering somebody. And pulling out a segment over there and passing it through the MLP. You're taking the collection of outputs and passing it through the softmax. But then this whole thing is just one giant network with shared subnets at the bottom. And so by having shared subnets, it became shift invariant. I could have this entire thing. It's really just a where the last command is just the output layer, right? And so I could just have written giant MLP, and you're good. So here's your first block. Three seconds, guys. Okay. So Pokemon Oddish, what is the answer to the first question? Is Oddish around? What is the answer to the first question? Okay, Oddish is not absent. Evie, what's the answer?
Sure.
True, yes. Thank you. And Beautifly, what's the answer to the second question? True, perfect. Thank you. So here we got it, right? So we can determine if a picture has a flower by scanning for the flower by with an MLP. And this is strictly the same as analyzing a large network with a single shared parameter MLP, right? Now, just for illustration's sake, I'm going to change the illustration because this is going to help, and this also shows up in your homework. If I'm scanning the input like so, I'm going left to right with these, with the image, right? And so this is the entire set of computation with the network. So this is the entire set of computations. But then when I illustrate it in this manner, it conveys the wrong impression. It conveys the impression that the black lines are in time order. Something to the right occurs before whatever is to the left. But then the yellow within each block, this yellow neuron is computed at the same time as this orange neuron. But that impression is not conveyed by this picture because of the yellow follows the orange in computation. So to give you the right picture, I'm going to draw each layer vertically, just to notify that that entire computation happens at one time instant, right? And so these two pictures are the same. And to simplify, I'm not going to draw so many arrows. I'm just going to draw a single arrow, which means that those two blocks are layers which are fully connected. Is the illustration clear to everybody? Right, okay. And so this scanning network is going to look like so. And this clearly conveys the impression that this is one feature vector at some point being computed by 3 neurons. At some time, this is being computed later in time, this is being computed later in time, and so on. Okay? And now, if I had this, if I were scanning, if this were the network over here, and this network was taking 2 steps at a time, it's said to be taking a stride of 2, because it's analyzing an input window with 2, then skipping by 2, and then analyzing the next window of input window of size 2, right, with 2. Whereas if it was stepping forward by just one time step each time, this is the computation that would be happening. This is a stride of 1. Do you see what I mean by stride over here? Right, okay. Now, how do you train this network? Once you decide that this is just a shared parameter network. Now that's easy. Training is going to be just like any other training. I'm going to give it a collection of images with and without flowers. And the network is shift invariant. All the lower subnets are identical. But here's the nice thing. Now when I give you images with and without flowers, I don't have to tell you where in the image the flower occurs. The entire network only performs the simple task of determining if there is a flower in the image or not. And so that's the only level of labeling that you actually have to provide. But then in order to train the network, you're going to have to make some changes to your training paradigm, which is this. You have to account for the fact that all of these subnets are identical. Now, when you have identical subnets, what this really means is that you have different components of the network which have identical parameters. And so you end up with the notion of a shared parameter network. So what this means is that, let's say I make an update, and I update the parameters of this copy of the network. That update must be reflected in all of these copies. If I update some particular element of this subnet, it must update all of the subnets, right? So how does that work? Let's see how updating with shared parameters works. Let's say I have a network. You can share parameters in any arbitrary manner, right? So let's say I have this shared parameter network where these two yellow connections are being shared, then if I look, so it can be anywhere. So let's say this weight Wij and WLMN have a common value by design, whatever the design may be. And so now that's, I'm just calling that common value Ws. And now, if I actually write the influence, draw the influence diagram, this common value Ws influences both these parameters because they're both actually identical to this guy. And each of them in turn is going to influence the divergence, right? So if I want the derivative of the divergence with respect to Ws, how many terms will it have? So how many terms will it have? Anybody? Pokemon, Arcanine, what is the answer?
It has like 4 terms, but like 2 paths.
2 paths, correct? And so the 2 paths are going to be d dive over dWijk times dWijk over Ws, and then d dive over dWLMN times the derivative of this weight with respect to Ws, right? That is the equation written over here. And now what is dWLMN over dWs? Anyone? Milk tank. What's the answer to that? What is the derivative of Wjijk with respect to Ws? Milk tank is not present. Okay. Venomoth. What's the answer? Yes. What is the answer? What is the derivative of this term with respect to Ws? It's 1, right? Because you're saying Wij equals WLMN equals Ws. So they're all common. So if 2 elements are identical, the derivative is 1, right? So in other words, the derivative of the divergence with respect to this common term is simply going to be the sum of the derivative with respect to Ijk and the derivative with respect to LMN. That makes sense? So in general, if you have a bunch of parameters which are all supposed to be identical, then the derivative with respect to the common value is simply the sum of the derivative with respect to all of the individual elements in the set that are supposed to have the common value. Okay? There's a lot of text on the slide. I'm just saying it in fewer words. So now, if I want to use gradient descent to train this network, the gradient descent algorithm would change like so. I know that my network has a whole bunch of shared parameters. For example, in the flower network, this red edge, and this red edge, they all come from, they're all the same edge of the subnets, right? And they must have the same value. So now, when I'm learning to update these parameters, I'm going to compute the derivative of the divergence with respect to each of these guys. And basically, I need the derivative with respect to the common shared value. And the derivative with respect to the common shared value is going to be the sum of the derivatives with respect to each of these guys, right? And so that term, this derivative, which is the sum of the derivatives with respect to all of the common terms that share that value, is what is going to be used in the gradient descent update. Everybody with me so far? Does this make sense? Yes, no? Yes.
Why would the derivatives not just like
Not?
why would the derivatives not just cancel each other out if you have one with the flower and one without the flower or something?
So the point is, we are just setting the derivatives to have a common shared value. Now, if it turns out that modifying perturbing, increasing the weight a little bit, decreases the loss in one case and increases the loss in one case, they could very well cancel each other out. But this is what the math says must happen, right? What will happen is that the derivatives in all of the places where nothing happens are going to be very small, because perturbing those will really not make any difference. And the significant derivatives are going to come from the locations where you do have the flower. Right? Any other questions? Okay. And this derivative, which is to say the derivative with respect to each of these terms, which have the same value, that is going to be computed using backprop. And so the story so far, position invariant pattern classification can be performed by scanning, 1D scanning for sound, 2D scanning for images. And this can be generalized to higher dimensional data as well. And scanning is equivalent to composing a large network and repeating subnets. And learning basically must be modified to combine the gradients from parameters which have the same shared value and before you perform the update. So, everybody with me so far? Now we're going to begin to get into some tricks. Now here's my figure again. That's a neural network. It is a 3-layer network, 3-layer subnet, right? Before we make the final decision. 4 neurons in the first layer, 2 in the second, 1 in the third. And now if you analyze any particular window of input, the first layer neurons compute 4 values, right? Then the second layer neurons compute 2 values using all 4 values from the first layer neuron. And the final neuron is computed from the output of the second layer neurons. This computation is performed at each location. And then all of these outputs are combined for the final output, right? Now, just suppose, I do the computation differently. The first layer neurons compute their output in the first window, and then without waiting for the second layer neurons, they go off and do their job and compute all of the outputs for the entire input. And then at the first position, the second layer and third layer neurons now pick up the computational outputs that the first layer neurons have already computed. Is this output at time 1 going to be different than if the entire network had first operated on that block before moving on? Is it going to be different? Pokemon Gengar? Or who's this? Pokemon Arbok?
No, it wouldn't change.
It wouldn't change, right? It would not change. And so, everybody agree that this would not change? No, okay. And so, the output here does not change because of the changed order of computation, right? Now, let me recurse this. Let me take the second layer neurons, since the first layer has already done its computation. And the second layer neurons are going to now be working on the output of the first layer neurons and process the entire input without waiting for the third layer neuron. And then, in the first position, the third layer neuron computes its output from the values computed by the second layer neurons. Is this going to be different than if I just done the entire computation in the first location? Politoed, Pokemon Politoed, what's the answer? Or Victre Ebel. This is Dia Dinesh. What is the answer to this one? Also absent. Most of you are absent. You realize this? Pokemon Goldeen. Oh my good God. Absent. Ariados. Pokemon Ariados. Lambert. What's the answer? Someone here? It should not be different, right? Okay. So the output here does not change due to the reordered computation. And so I could just do this and things will not change. Right? What have we done here? We've just reordered the computation. So here's what we were doing earlier. We were scanning left to right. At each position, we were pulling up a segment, and that segment was being passed through the MLP, and the output of the MLP was being passed through the softmax, right? Let me expand it out. So at the first layer, you're pulling out a small window of the input. That's the window of the input that you're analyzing. And then you're using that window to compute an affine value and passing it through the activation. And then this rest of the, and for subsequent layers, you're always working off the output of the previous layer, right? This was scanning. You're scanning, and then when you're scanning at each location, you're going through the layers. So at each location, you're going through the layers. And at each layer, you're computing an affine value from the output of the previous layer, and then finally applying the activation. Now, where is the bulk of the computation being done? In fact, the entirety of the computation is being done inside the innermost loop, right? So, if I change the order of these loop indices, will it change the final output? Yes or no? Right? That's basically what we did. All we did was change the order of the array indices, the loop indices, and we know for certain that the output is not going to change, right? Same thing with, if I'm doing this with a, on 2D images. At each location, the entire window is being passed through the network. And, the network is computing its output at each location. And then the outputs of the subnetwork at all the locations are finally being passed through a softmax, right? Or maybe an MLP. But if I change the order of computation, if the first neuron in the network just went off and computed all of its outputs and arranged them in the same shape as the input itself, right? And so in fact, I could do this with all of the neurons in the first layer, okay? If I do this with all of the neurons in the first layer, now the neurons in the first layer have just gone off and computed their own thing. They've arranged their outputs in the same shape as the input. And now, if I want to perform classification of this block of the image, all I really need to do is to pick up the values computed from this block by the neurons, right? Which are these 4 red dots. And I can pass those 4 values at those 4 red locations through the rest of the network. And I get my final output. And I'm going to get the same output as if I had simply used the entire, focus the network on that block, right? Everybody agree with this, right? And so, in fact, I can recurse the logic over here. After the first level neurons have done their computation, the second layer neurons, both of them in this case, can go and compute their outputs for each location of the input by simply reading the corresponding locations from the maps produced by the first layer neurons. I'm calling them maps because they're arranged in the same manner as the input itself, and they're basically forming a map of detections by the first layer neurons, right? And so I can just do this. And now if I want to classify this little block, I just have to pick up the corresponding locations from the outputs of the second layer neurons and pass them through the softmax and I'm done. Everybody agree? You guys, yes or no? Okay. And so we can do the same thing. We can create a map for the third layer neurons as well. And this is a flower detector. This map is a flower detector for each location in the original image. And so now, if I want to know if there was a flower in any specific location, I just have to go and read the map value off from the final map, right? So, and then I can put this whole thing through a max or a softmax or what have you to make a picture level decision. So what am I doing here? Once again, in the original scanning, I'm going left to right, top to bottom. At each position, I'm pulling out an image section and passing the section through an MLP, right? So if I were to expand that out, I'm going left to right, top to bottom. At each location, I'm passing that block through through all the layers of the network, starting with the first layer, and then finally making my decision, right? And then once again, the first layer is going to be reading a block of the input. Subsequent layers are simply reading the outputs of the previous layers, right? And where is the action again? In the innermost loop. So what did we do when we changed the order? Again, we just flipped the order of the indices, right? We moved the layer index out to the top, and we moved the scanning loops into the network, into the inner loop, right? And so what we are doing now is scanning. Each layer is scanning the input, and then every subsequent layer is scanning the output of the previous layers. But we know that the output is not going to change, right? The first layer is scanning the input, every subsequent layer is scanning the output of the previous layers, but the overall output is not going to change. And so this is the reordered computation, right? And we know that this will work. So any questions?
Why are we switching the order of this?
Why are we switching the order? We will see in a bit, okay? But switching, so my point is, if you switch the order, it doesn't change anything. But then when you switch the order, this business of scanning with an MLP gets a new name. Anybody want to guess the name? You've heard the term? It's a convolutional neural network. This business of scanning is called convolution. All I've done, it's exactly the same as scanning with an MLP and then taking a decision over the collection of outputs. But if I change the order in which I perform the computation, it gets a new name. It becomes a convolutional neural network. Everyone with me? Okay. So what we've seen stories so far, position invariant pattern classification can be performed by scanning the input for a target pattern. Scanning is equivalent to composing a large network with shared subnets. And the operations in scanning the input with a full network can be equivalently reordered as scanning the input with individual neurons in the first layer to produce scanned maps of the input, and then jointly scanning the maps of the previous layers. Again, this is very important, right? There isn't a single map at this point. Each of the first layer neurons has produced a map. Second layer neurons, we're looking at all 4 maps simultaneously because they're going to be looking at the outputs of all of the first layer neurons. Third layer neurons, we're looking at the outputs of all of the second layer neurons simultaneously because they must be looking at the outputs of all of the second layer neurons and so on. So you are jointly scanning the map of outputs by all the neurons in the previous layer to compute the subsequent layers, right? Here's your second question. 5 seconds, guys. Okay. Pokemon Puchiena, can you answer me the first question? The Zihan gang.
True.
Okay. Thank you. And Lotad Yishuyen. I don't know if I'm getting the pronunciations of the Pokemon right. What is the answer to the second question? That's it. Okay. Pokemon Gloom.
Hi, it's true.
Okay. The Pokemon. So both statements are true. Right, everybody agree? Okay. So what is happening over here? The entire MLP looks for flower-like patterns at each location, right? So the neurons in the first layer, but if the entire, when I'm scanning with an MLP, the entire MLP is looking for flower-like patterns. But the way we posed it, the task of looking at the entire input window has been taken up by just the first layer neurons. The first layer neurons are looking at this window of input, and then subsequent layer neurons are simply looking at the output of individual first layer neurons, right? And so what happened here was that these guys ended up looking at the entire window, and this fellow here only looked at this one dot. And this fellow here only looked at this one dot to decide if this block had a flower. Now, I can change things up a little bit. How so? I can distribute the scan. Instead of having the first layer, and I'll explain why this makes sense, right? So instead of having the first layer neurons look at the entirety of the input, and the second layer neurons just looking at one dot each from the 4 maps, so I can have the first layer neurons look at a smaller window of the input like this one, and then scan the input with this window to create their maps, right? And now, if the second layer neuron looks at a small window of the inputs of the outputs of the first layer maps, what is the second layer neuron looking at now? Yeah, what is a collection of small maps representing? Pokemon Togetic. What is the collection of, what is this collection representing? Okay, Togetic is absent. Dragonair? Pokemon Dragonair? No? Okay, Pokemon Raichu?
Yes, sorry.
Okay.
All
right.
It should represent the image, like the upper left of the image.
Perfect, right? When you're looking at this little map of pixel values output by the first layer neurons, you're looking at the combined region that of all of the combined, the union of all of the regions represented by those individual values, which is this larger window. Make sense? Right? And so now, instead of just have the first layer neurons can look at small regions, and the second layer, because the first outputs of the first layer neurons have been arranged in the form of a map, the second layer neurons can actually look at a small window or small windows from the outputs of all of the first layer neurons and compute the outputs, and they're going to be looking at a larger region of the input, right? And now, what this does is it allows you to say, so one way to think about it is that when you're performing something like this, if I'm doing this, where I have the entire job of looking at the input being designated to the first layer neurons, the first layer neurons must look for flower-like patterns in their entirety, right? Whereas I know that flowers are composed of things like sepals and little pistils and so on, and these have, what happened? Okay, and these have repetitive structure. A sepal or a petal occurring in different locations pretty much looks like a petal or a sepal, right? And so this, what is happening here now is that the smaller window is looking for sub-patterns of the larger pattern, where the sub-patterns may have repeating structures. And then in doing something like this first layer, second layer neuron is looking for a flower-sized image, but it learns that maybe you should be looking for patterns. So I have 4 first layer neurons, right? So maybe the first neuron looks at things like petals. The second thing looks like something like pistils. The third looks like something like stamens, right? And so this neuron is learning to say, I should fire if I find something like a petal in the top left, something like a stamen in the middle, and something like a pistil in the bottom right, right? And so it's learning complex combinations of the units being detected by the first layer neurons. That make sense? Good. Everybody?
Yes.
Okay. Can I hear a combined yes? Yes. Thank you.
Yes.
Thank you, guys. Appreciate it. And so, basically, if the second layer neurons scan the input, scan the outputs of the first layer neurons, they're effectively scanning the entire input with this big window, right? And what is the obvious next step? What would the obvious next step be? I can recurse, right? And I can say, of course, over here now the next layer neurons would be scanning the maps output by the second layer neurons. But if I were to, but even before recursing, I want to point out that none of this has changed the basic fact that it's still scanning with a shared parameter network. That story has not changed. You are still scanning with a shared parameter network with one minor modification, and that modification is that, now just consider this. The first layer neurons, let's say I have this network where I have 3 unique first layer neurons. Now if the first layer neurons are looking at smaller windows of the input, then the first layer neurons are effectively, in analyzing the input, in analyzing this region of the input, I effectively have 9 copies of the black neuron. I have 9 copies of the red neuron, and I have 9 copies of the blue neuron. Right? And so the first layer neurons now have this structure, which means that in analyzing the input, these 9 have shared parameters, these 9 have shared parameters, and these 9 have shared parameters because they're just copies of the same neuron, right? But the second layer neuron is basically looking at the lot of them. All parameters downstream are unique, but only within the first layer. I have 9 copies of one set of weights, 9 copies of a second set of weights, and 9 copies of a third set of weights. So I'm still scanning with an MLP, but within the MLP, I have further parameter sharing, in that within the first layer, I have these copies of parameters. That makes sense to everybody? Can you wave if it made sense? I see a lot of dopey faces. It's early in the morning. Thank you. I can't see if the guys on Zoom are waving. Okay. So, and now I can recurse this logic. The first layer neurons can be looking at even smaller regions, right? And scanning the input and creating their maps. And then the second layer neurons could now be looking at windows of the first layer neurons. And when they do so, they're looking at a slightly larger region of the input itself at each position. And now the third layer neurons could be looking at windows in the maps of the outputs of the second layer neurons. And in so doing, they're looking at an even larger region of the input. And so I'm building the pattern now. Earlier, the entire pattern was being detected by the first layer neurons, and I was just building up logic over the subsequent neurons, right? Here, I'm distributing the pattern detection. Shunhei, you want to go wash your face or something? Please do that. You good? I know it's very early in the morning. I know you guys have been pulling all-nighters. It's cruel, but then I have no choice. This is the slot I have, right? Okay. So what we are doing is building up this pattern over many layers. So it's a distributed scan. Instead of scanning for the entire pattern in the first layer and then building up logic, you're distributing the scan itself. So this is a distributed scan. Nonetheless, and the final classification of the entire image is basically viewing outputs from all locations, but this still remains scanning with a shared parameter network. So when I do this business of distributing the scan, if I go and draw all the commonalities, you're going to find that I'm scanning with a shared parameter. I have a very ugly picture over here because it's very hard to draw these pictures properly. So if I go and look at the code, what changed? The pseudocode. Earlier, what were we doing? We were scanning the input, and then at each location, we were going through layers, right? And at each layer, the first layer looked at the entire window. So I had this special logic for the first layer. If you go back and look at the previous pseudocode, we had this. We can go back a sufficient number of slides. If you look at this previous pseudocode, for the first layer, I was actually looking at a block of the input, right? Subsequent layers, we're looking at just one position. So I needed special logic for the first layer. Subsequent layers would actually be just one position. As it turns out, this crazy business of distributing the scan actually makes the pseudocode simpler. Like so. Right? Because at every layer, you're looking at a window of the map computed by the previous layers. This thing, is the pseudocode clear to everybody? This is the original, wait, not this one, sorry. This is where I was scanning. Now, earlier, when I'm scanning without distribution, this is what I was doing. When I was going through the layers, for the first layer, I was actually pulling out a segment, right? A window. Otherwise, I was just looking at a single pixel from the previous location. And now, and that's what we reordered, right? And now, the code is simpler. At each position, I'm just picking out a window of values from the output of the previous layer neurons and then computing my affine term and applying activations. So once again, within each layer, I'm scanning the input. When I'm scanning at each location, I'm pulling out a window. There's no if clause over here. This is what happens at every layer, right? And that window is actually being, and the size of the window will be specific to the layer. And that window is being used to compute the affine term and the subsequent activation. Questions? Questions, anybody? Okay. Very clear. Okay, so this operation of scanning with a window, this is called a convolution, which is why we're speaking of a convolutional. This entire operation is a convolutional neural network. Okay? Same thing. Yeah. So in 1D, it's going to look something like this. You'd have a network of this kind. If you are trying to analyze this broad window of input, if you didn't have the distributed scan, the entire network is going to be computing, looking over the entire window. But if I'm distributing the scan, the first layer neurons would be looking at a small window of the input and creating their maps. The second layer neurons are going to be trying to look at, want to expand out the region of the input they're looking at. So they would actually be looking at a window of the outputs computed by the first layer neurons, right? And now the third layer neuron want to look at an even wider region of the input. So they're now going to be looking at a window of the outputs computed by the second layer neurons. So this is a convolutional neural network which is scanning in 1 dimension, whereas for images you are scanning in 2 dimensions, right? So, and the final perceptron aggregates evidence, like does this recording have the word welcome? When you're scanning in 1 dimension, you call it a time delay neural network. When you're scanning in 2 dimensions, you call it a convolutional neural network. But a time delay neural network is also often called a 1-dimensional convolutional neural network. So a TDNN is the same as a 1D CNN. Okay? Thank you. Anybody want to guess how many slides we've been through so far? 228. So it's been a fast-paced class without conveying too much information. It's magic. Okay. Pokemon Celebi. This is Nithya Kemp. Okay. Is the first statement true or false? Nithya? Are you here?
It's false.
No. False. Okay. Second one, Pokemon Wartortle. That's Jocelyn. True or false?
True.
True. So, Pokemon Butterfree. True or false?
True.
Third one. True. Pokemon Fortress. Fourth statement. True or false?
True.
True. Okay. Thank you. Everybody agree with those answers, or do you have any difference of opinions? The first and the last statement are false. Only the second and third statements are true, right? So non-distributed scanning requires the output maps to be arranged in the same shape as the input. You don't, because you're not looking at windows, right? It's only when you're looking at windows, it doesn't really matter how you arrange it. Now, if it's distributed scanning requires the output maps to be arranged in the same shape as the input because you're looking at windows. Otherwise, things get very hard. Right? So far, so good. Everybody agree with these 2 answers? Okay, yeah.
Question. So when you say the same shape, do you also mean the same dimensions or just?
The dimensions might shrink, but it's going to be the same shape, right? So see, look at that. If I have a stride of 2, for instance, it's going to shrink by half in each direction. So why distribute? Yeah.
So the window size remains same for the layers?
No, we can change. Right. Because the size of the pattern that you're searching for, it can change.
So that's specified in the requirement?
The window size must be specified as part of the design.
Okay. So it does not have to remain constant, right? As a constant layer 1 to layer 2.
The second layer can be a completely different window size than the first layer. Right. But when you're scanning, the window size obviously is going to stay the same through the scan. Now, Distribution, there are multiple reasons for distribution. Distribution forces hierarchical representation with localized patterns in lower layers. It results in fewer computations and far fewer numbers of parameters. Let's see how each of these works, right? Remember when we went back, way back when we were trying to build up this double pentagon decision boundary. Did we try to build the pentagon all at once in the first layer? That ended up requiring a tremendously large number of neurons, correct? So how did we do it? We've had the first layer neurons detect individual edges, and the second layer neurons combine them into subparts, and then we combine those subparts into the whole. This kind of distribution ends up being far more efficient because otherwise, as we saw way back when, you're going to require a great many more neurons to capture the same pattern. So distribution of the pattern has a benefit over here. So we must encourage such hierarchical learning because it's data and parameter efficient. Now, what about fewer computations and fewer parameters? Let's look at fewer computations. So let's say I'm scanning without distribution. So then this would be the entire network. I'm doing a 1D scan over here. This would be the entire network. And these are all the values that are going to be computed when I'm scanning the input. Is there any value at all which is guaranteed to be a repeat at any position? That is guaranteed to be a repeat of a computation from another position in this compute? Every single number is unique, is it not? Yes or no? Some enthusiasm here? Yes or no? Thank you. Okay. So I'm just going to show this as a simplified figure. Non-distributed scan of an 8 time step wide pattern with a stride of 2 time steps in this example. All of these values must be computed, right? Now, and the number of parameters, if I'm looking at a width of 8, and if I have N1 neurons in the first layer, N2 neurons in the second, and N3 neurons in the third, then I'm going to have, D is the depth of those little black bars. So each black bar is size d. So if I'm looking at a width of 8, it's 8D terms. 8D times N1 parameters from the first layer, N1 times N2 parameters from the second layer, and N2 times N3 parameters from the third layer, without even counting the biases, right? That's how many parameters we will need. Now, if I only need to compute it for one column because all the columns are identical, right? Now let's do this with distribution. So let's say I'm still looking for a width of 8, but then I'm doing this in a 2-step process. I'm distributing the width of 8 over 2 layers. The first layer consists of a layer of neurons which looks at windows of size 2 and takes a stride of size 2. So I'm going to have 4 computations with the same network. And then the next layer is going to look at the outputs of at 4 positions from the first layer neurons, which gives me effectively a window of size 8 at the input, right? So now, assuming that I'm still scanning and I have a stride of, say, 2. So now let's first count the number of parameters, right? In the first layer, you got a great reduction in the number of parameters. Earlier, you had 8D times N1 parameters, right? Now, you just have 2, you're just looking at a width of 2. It's 2D times N1, right? The number of parameters changed, reduced because I'm reusing parameters. So that was convenient. And because these are all the unique parameters over here, right? Everything that's highlighted. And earlier, you needed all 8 of those things at the in the first layer to be unique. Secondly, so if you begin comparing them, it's very easy. You can look at the slides. The number of parameters is going to be much fewer when you distribute the scan. But here's the bigger benefit. Look at what's happening. When I'm computing the output at the first position, all is fine, right? This is exactly as before. But then when I'm computing the output at the second position after a stride of 2, do I need to perform all the computations, or can I reuse some of the computations that I had in the first position? I can reuse those 3 guys, right, which are overlapping. And so suddenly the amount of compute that I will need is going to be far lesser, right? As you can see. Now, so this reuses the outputs of 3 of the layer 1 blocks in the first location. In fact, at every location, you're only computing one new block, and that block is small. So the amount of incremental computation per location has suddenly gone down by a factor of 4 in the first layer, right? Suppose I distribute this now over 2 layers like so. So now I have one layer of neurons, which is 2 blocks, which has a width of 2, a window of size 2, scanning the input at the first layer. And so this is the first layer. And then I have a second layer of neurons, which has also got a width of size 2, scanning the outputs of the first layer neurons. And then this third layer is looking at a window of size 2 from the second layer neurons. What is the overall window size that you're looking at each position? What is it? So, Pokemon Marib, that's Maxwell Fang. What is the overall size of the input that you're looking at the input? Absent, okay. Delibird, Atharva. What is the overall size of the window that you're looking at the input?
You're looking at 8 time steps.
8, so looking at 8, right? And so you still got a window of 8, but the number of parameters, unique parameters, is restricted to these guys, which is much smaller in number than when you just had one single network, right? So compared to these, you will see an order of magnitude difference very quickly. In fact, several orders of magnitude difference. And again, you can see that if I'm using a stride of 2, not only am I reusing, so yeah, so the first compute shows you all of these highlighted, the colored ones. So you'd be computing all of these, they must be computed. But when I take a stride of 2 and go to this position, this fellow can just reuse these 2 computations, right? This fellow can reuse this computation. So the compute has gone down. When I go to the third position, I can also reuse this pink bar. And so by reusing the computation in this manner, I'm actually using far less compute than I would if I were doing the whole thing in one shot, right? So does this answer the question about why scan and why distribute? Why reorder? If you were not reordering things, you could not take advantage of this. If you were reordering things, if you didn't reorder, you could still take a benefit from the reduced number of parameters, but you cannot get the benefit of reused computation. That's why we reorder. Make sense to everybody? Okay. So in the third position, all of these 3 guys are going to be reused, right? And this is with a stride of 2. If I had a more dense network of this kind, then here's going to be the number of unique parameters, still very small. And if you look at how much you would reuse in each position, you'll find that the amount of reuse actually increases a whole lot, right? As the network gets more and more complex, the number of computational terms that you will reuse increases rapidly, right? So same thing over here, right? Regardless of whether I was doing it in 1 dimensions or 2 dimensions, you're going to get the benefit of reusing computation, right? Reusing values. So I'm not going through the 2D example, just look at those in the slide. So, but then, why distribute? The key intuition is that regardless of the distribution, we can view the network as scanning the input with an MLP. The only difference is the manner in which parameters are shared within the MLP, but this results in this in one benefit, which is you get the benefit of shared parameters is that you get fewer numbers of parameters, and the benefit of reordering the compute is that you get to perform a whole lot less computation for the same output, right? So Did all of that make sense? Is everybody with me? Yes, no? Give me an enthusiastic yes, please.
Yes.
Thank you. Guys on Zoom, give me a yes.
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 All right. So here's the story so far. Position invariant pattern classification can be performed by scanning the input for a target pattern, which is equivalent to composing a large network with shared subnets. The operations in scanning the input with a full network can be reordered as scanning the input with individual neurons in the first layer to produce scan maps of the input, and by jointly scanning the maps output by all the neurons in the previous layer and in subsequent layers. And the scanning block can be distributed over multiple layers of the network. So this results in significant reduction, not just in the total number of parameters, but also in the compute, because we reuse a whole lot of computation. It's not on the slide, I should add it. Somebody take it. 5 seconds, guys. Okay. Pokemon seeking. Is that first statement true or false?
It's true.
Thank you. Pokemon Golbat. Second statement.
It's true.
Thank you. Slowking. What about the third statement? Slowking is absent. Okay. Pokemon Lugia, that's Agent Kim. Is the third statement true or false? Porygon 2, that's Shijie Bian, was the third statement true or false? There are more people absent than present. Thank you.
It's true.
It's true. Okay. And Mohammed, the fourth answer, fourth statement. False. Okay. So just the fourth statement is false, right? Everyone agrees that. Thank you. So distributed scanning enables hierarchical composition of patterns, which results in more generalizable models, as we saw. It results in greatly reduced number of parameters, and it provides computational advantage through reuse of computation. And it does not reduce and does not result in reduced memory requirement. You compute the same number of terms regardless. So some final touches before I wrap up for today. I was just introducing the notion of CNNs and where the logic of CNNs actually comes from. That convolutional neural networks are basically exactly the same as MLPs, with the distinction that you want position invariance. And so instead of just having one thunk MLP looking at the input, you're scanning for the pattern. And you're combining the decisions at each position, and the scanning results in shared parameters, reduced computation, and because you have shared parameters, you also need a far smaller amount of training data. So if I didn't have the scanning, then I'd have to provide training data with flowers at every possible position. And I'd have to have a correspondingly large network to learn to classify if pictures have flowers or not. By scanning, I don't need pictures with flowers at every possible position, although diversity is a good thing. I mean, if you always presented training images with flowers in the top left corner, that is never going to generalize. The idea is that your pictures will have flowers in different positions, but you don't need to have the entire range. So you can have a much smaller variety of training data, right? And a much smaller amount of training data, and you get to exploit the commonalities in all of these for improved models and improved computation. So let's get through some final terminology: receptive fields, scanning with strides, and accounting for jitter, right? So again, Just as a perspective, the entire operation can be redrawn as before with maps of the entire image. Each neuron scans and redraws the input with some features enhanced. This is one way to look at it, right? Remember, a neuron is just looking for patterns, right? So you can think of the first layer neurons as, maybe a neuron is looking for a petal, and it's scanning the input, and that map is essentially redrawing the input with the petal highlighted. Maybe the next neuron is looking for a pistil. It's scanning the input, and it's highlighting those regions of the image where the pistil has occurred. So, and then the second layer neurons. So the first layer neurons would be scanning the input and creating maps with patterns highlighted. And the second layer neurons are going to be scanning the outputs of the first layer neurons, which is effectively also scanning the input. And so it's going to highlight more complex patterns. The second layer neurons are repainting the image with more complex patterns highlighted, right? And the third layer neurons, which are looking at windows of the second layer neurons, are also looking at much larger windows of the input, and they are going to fire whenever the patterns that they are looking for in the second layer neuron outputs show up. And so they are going to be highlighting other patterns in the map that they generate. So that's one way to look at it. And the specific patterns that each of them highlight, the size of the window that they look at, and the specific patterns that they highlight, they're called the receptive field of the neuron. So the receptive field of the first layer neurons is a small window in which it's looking for some patterns. And first layer neuron receptive fields tend to be very deterministic. I mean, a first layer neuron is looking for just maybe a petal. Second layer neurons have a receptive field which is slightly larger. And it's a little less deterministic because it's not looking for a unique pattern. It's looking for, we know that we can perform ORs with neurons, right? So which means it can highlight and fire for different combinations of first layer patterns. So it's not easy to just look at the set of weights of the second layer neurons and determine what they're looking for. And similarly, third layer neurons are going to have a larger receptive field. They're looking at a larger region of the input. And it's even more difficult to determine what exactly it is they're looking for. Nonetheless, they all have some combinations of patterns that they'll fire for. So the receptive field for a neuron refers to the region of the input it's looking at, but also to the kinds of patterns it's looking for. Right? And so each of these scanning neurons is generally called a filter. It's called a filter because this business of scanning is called convolution. And so the term convolution is derived from signal processing, and what you actually convolve inputs with is called a filter in signal processing. So these neurons are also called filters. Each filter scans for a pattern in the map it operates on, and the size of the input and the pattern it's looking for is called the neuron's receptive field, right? And for higher layer neurons, it's not obvious what the receptive fields, the patterns are, they must be calculated. There's this notion of flattening. Typically, the map produced by the final layer neuron is passed in its entirety to a softmax or an MLP. So you don't need to present it in the same shape as the input because the subsequent ones are looking at the entire input. You can just reorder these multidimensional inputs as a single vector. So this is a term you might encounter, that's flattening, where you take that something that's in the shape of an image and just reorder all the values in the shape of a single vector, right? And the other thing is stride. How much do you stride by when you're scanning? So when you're scanning, you can move by one pixel at a time or one position at a time, or by multiple positions at a time. So how much you move by is called a stride. And the size of the output map is going to be scaled down by a factor that equals the stride. If you move forward by one position at a time, the output is going to be pretty much the same as the input in size modulo some edge effects. If you're moving forward two positions at a time, the output is going to be half the size. So the stride affects the output size, right? And so you can have any stride at any layer. These end up being design choices. So a CNN with strides, when you're scanning, instead of scanning one step at a time, you're going to be scanning with a stride, right? Another significant modification is modification for jitter. I'm building up a flower by looking up, when I have a distributed scan, I'm building up a flower by looking for its parts. Does it have petals? Does it have sepals? Are the petals in the right place? Are the sepals and are the stamens in the center, right? You're looking for the right pattern in the right position. But if a petal has moved by like 1 pixel, does that suddenly mean it's no longer a flower? A small jitter should not affect the overall pattern that you have detected. And this is particularly important when you're decomposing the larger pattern into sub-patterns. So we like to introduce some jitter invariance. And this we do through some action, an operation called pooling, which says that if I'm looking for a petal not just in this location, but somewhere in this region. So you can think of this as a petal detector, and it must tell me if a petal has occurred in that region. How would we do this? We just did this for the entire flower, did we not? Yes. So how would you do it? Can you say that aloud? No, how did we do it for the flower? We scanned for the flower. How did we combine those decisions to decide if there was a flower? We ORed them. We took the max, right? You can do that at a smaller relay scale to decide if there's a petal in the block, right? That's called pooling. That makes sense? Right? We're doing the same thing repeatedly. So.
You have a slide of what does it like a jitter invariant then?
No, you're not, because you can still, because again, remember that way back when, and this will probably go a minute over, just bear with me guys, and we're done literally. But when we distributed the scan like so, we should ask difficult questions early on. So we said, where is that picture? You're learning some specific patterns, right? So you would work, regardless of the scan, you might learn that the second layer neuron looks for, okay, skip it. There was I. The second layer neuron looks for a petal in the first position, a petal in the second position, a sepal in the center, things like that, right? You want that, if you want to say that it's not necessarily a petal in this position, but somewhere in this region. That's regardless of the stride, right? And so how exactly would you perform this jitter invariance? You're going to pool. So you look at windows of the maps produced by the first layer neurons, and you're going to replace you're going to pick the largest of those and copy them over. And so at each position, you're going to be picking the largest, or there are other operations of pooling. And this is a step that is performed immediately after convolution, after the convolutional layer, to give you a modified map which accounts for jitter invariance, and subsequent layers are going to operate. So the overall structure that you have, with all of these individual neurons computing maps with possibly pooling operations in between, this is called a convolutional neural network. So I'll stop. So yeah, we'll look into convolutional neural networks in more detail in the next class. I was just introducing the basic concept of how they come to be from a computational perspective. In the next class, we're going to go back and look at them from a biological perspective, because when convolutional neural networks were first invented, there were two groups of researchers looking at it from two different perspectives. And the second group looked at it from biology, and we'll see that in the next class. So.